I'm Stavros Vatikiotis, and I'm a researcher at Athens University of Economics and Business at the Department of Management Science and Technology. I completed my PhD studies 3 months ago, and they were supervised by Professor Yannis Mourtos. And today I will present part of my PhD thesis related to production scheduling. So I have included some background regarding optimization methods, which may be distinguished in main three categories. We have exact methods like linear programming or constraint programming. And these are techniques which guarantee that they will eventually find the optimal solution using mathematical models. And in terms of their advantages, they guarantee that they will find the optimal solution, of course, needing much time. But even when they don't find the optimal solution, they provide bounds for solution quality in terms of responding to the question whether the solution found is good or bad. On the other hand, these methods are known to be quite expensive, especially on large size instances, and also they require long run times in practice. On the other hand, we have heuristics, which are strategies which are designed to find good solutions quickly, mainly exploiting some kind of rules. And they're usually fast and quite efficient. They're easy to implement. But on the other hand, they do not provide these optimality guarantees that the exact methods provide. And their performance mainly depends on the problem and the data and so on and so forth. Somewhere in between, we may find meta-heuristics like genetic algorithms or simulate annealing or local search, which are, again, strategies, but they operate in a much more guided way. And they are flexible, and they are quite suitable for large-scale problems. But on the other hand, again, they do not guarantee optimality, and a quite important issue is that they require tuning their parameters. In terms of scheduling, the goal of scheduling is to decide upon assignment of jobs to machines, and then having this assignment, the jobs need to be sequenced. And commonly, scheduling problems are described by the environment. We may have a single machine or parallel machines, or even SOP environments like environments which have multiple stages, one after the other. In terms of the properties, we may see machine eligibility, setup time, splitting or resources. And in terms of the objective, the most common objective and the one related to today's presentation is make span, which refers to the completion time of the whole schedule. In terms of data, scheduling and optimization are known to be quite data intensive and data hungry. So at first, we would need the set of jobs and, of course, a plant layout with the stages and the machines. Then we need the processing times, which refer to the time needed for a machine to process a specific job. And finally, we also need any other data related to specific properties, for example, the setup times or the resources. This is a more visualized example. What we want to do essentially is to create a Gantt chart like the one shown here. This is actually an optimal solution. And the data requirements are, of course, the processing times per job or per machine, and also the setup times for this particular example. To show how the methods may interplay with one another based on the problem, I have also included this example. So we may have a simple scheduling problem with 20 jobs on 3 parallel machines and with no setup times. And the objective is the make span, which is known to be the easiest one. So we know this problem is solvable using an exact method, and it is solvable in quite a few seconds. On the other hand, when this problem is extended to add setup times, these setup times require sequencing constraints, which are addressed by the big M constraints. And these constraints are known to have a severe effect on the bounds for the MILP. On the other hand, constraint programming formulations are known to be better suited for sequencing and also handling of resources. So we may consider a hybrid approach, where MLP would do the job assignments, and then we may have a second part where the constraint programming module will deal with the sequence. On the other hand, when instances get quite large, like 1,000 jobs on 50 machines, the most common strategy is to design meta-heuristics, which will guide the solutions, the solution sets within the search space. And then in some parts, we may integrate some smaller pieces of MLP or CP components. So today's problem is the makespan minimization on the hybrid flexible flow shop scheduling problem. And this problem has been inspired by an actual case within MODAPTO, and it refers to the production scheduling for a motor manufacturing company. So to describe the problem, we have a set of orders, and each order is associated with a different set of jobs, which need to be assigned on sequential stages. Each set of stages consists of identical machines. We have the processing times, and jobs are allowed to skip stages because not every job needs to get through the operation that each stage is assigned to. Then we also have a really practical constraint where jobs within the same order need to be processed consecutively. And this constraint originates from the packaging constraints due to the limited capacity of warehouses. Then we have transportation times, and these times refer to the time needed to move one job from one stage to another. And due to the different layout, these transportation times are known to be machine dependent. And finally, the most challenging property is that each machine has a buffer, which is like a temporary storage place, both on the entry and the exit. And each buffer has a limited capacity. So overall, we focus on the job scheduling problem on an HFFS with machine-dependent exploration times and limited capacity buffers under the makespan objective. This is a more visual example regarding the problem. On the left, we see the table with orders associated to the jobs. And on the right-hand side, we see how the layout of the problem looks. And for example, we may see that we may move from stage 1 directly to stage 3 without going through stage 2. So in terms of the literature review, the first close variant of the problem that we've seen was 10 years ago. So we see that it is a quite fresh problem, but in the recent years, we see that there is a quite increasing interest on it. And from our side, we move beyond state-of-the-art literature in two aspects. The first one is that we consider all these complex properties which are left out on the previous literature works. And we are also aiming at solving quite larger instances of quite larger size, namely up to 315 jobs on 9 stages. So in terms of the solution method, our first idea was to create an exact method, an MLP formulation. But the problem with this formulation is that when we try to include resources, and in our case, limited capacity buffers, it is required that we insert time intervals, which explodes the size of the problem up to a point where it is impractical or inefficient. So what we did is to split the problem in two parts. So we have the first part, which deals with the assignment of jobs and the sequence of jobs on machines. And we have a second part, which deals with the resources being the limited capacity buffers. And for the first part, we have proposed 5 different meta-heuristics. Very briefly, we have a genetic algorithm for a GA, which is a meta-heuristic algorithm which is based on representing solution in the form of chromosomes, and at each iteration, the best ones survive. We then have the particle swarm optimization, which imitates, and it is based on the movement of birds within a flock. Then we have a very typical local search, which starts with an initial solution and then tries to explore the neighborhood being the closest solutions to it. We have also a taboo search, which has a similar logic to the local search, but it avoids visiting already examined solutions, which are stored inside the taboo list. And finally, we have a simulate annealing algorithm, or SA, which is whose main advantage is that it is willing to accept worse solution under some probability, with the aim of getting to better solutions as the solution search space goes on and on. For the second part, we have a constraint programming formulation, which is enforced to respect the assignments and sequences made on the first part. And then what it does, it actually adjusts just the start and completion times in order to respect the capacity of the buffer. Solutions in our approach are represented in the form of a sequence like the one shown on the top. However, we need to evaluate these sequences. And in order to do that, we have to assign and sequence jobs on each machine. And very briefly, what this procedure does is that it starts with the first order in the sequence, and then it gets the jobs within this order. And then for each job, it assigns greedily on machines which have the least load. This is the CP formulation. Again, very briefly, what it does is that it enforces that jobs and sequences are respected, but then it just opens the intervals to respect the buffer's capacity. What we've seen on the benchmark experiments, and these are the efficiency results, is that there's no clear winner between the algorithms, which is either a good thing or a very bad thing. Overall, we may see that the methods that seem to be better are the GA, taboo search, and on some instances, the local search with kind of similar computational times. However, we also need to examine these results from another perspective, as we need to see at which point of time within the whole execution of the algorithm the best solution was found. And here we see that the taboo search needs more time to actually end up with the best solution, while the genetic algorithm seems to be, on this perspective, a bit better. We also try to hybridize these methods in order to leverage the advantages that each one has. So we started with devoting 10% of the total time to the SA in order to exploit its ability to provide diverse solutions. Then half of the time of the total experiment was devoted to the GA, and in order to evolve solutions and improve what we already had. And finally, we also employed the taboo search, which got the best solution found from the GA and tried to improve it. And again, what we saw here, what we observed is that, again, okay, hybridization method does offer some improvements, but they are not quite impressive. So in terms of the next steps, we have two main directions that we are currently working on. The first one is to exploit whether hybridizations between the exact methods, the MILP that we already have at hand, and the CP may be used in parallel in order to get better solution. And there are three different ways to obtain this. The first one is to provide this fixed sequence of jobs that we previously saw, but without assigning and without sequencing, and we would let the constraint program formulation to decide. Then we may also explore that we have this fixed sequence and we also assign jobs on machine, and CP constraints are activated in order to handle the buffers and the sequencing. And the final one is actually the approach that we already have, is to decide on the first part with the assignment and the sequencing of jobs and activate CP only to handle the buffers. Last, we also consider the implementation of a quite trendy metaheuristic named adaptive large neighborhood search, or ALNS. And what it does, is that it destroys a part of the solution, and then via another method, commonly a CP, it tries to reassemble the solution, and it is known to perform quite well due to the diversification from the distraction operators. And we are also have several ideas on this problem, and they mainly consist of workforce planning, as this is something that has not been addressed on the current status, on the current point of our work. The first one is worker availability constraints. So we have a limited set of workers available, and we have to ensure that in parallel, no more than these upper bound workers are used. And this is something that we have done in the past, and it is something that we're quite comfortable on doing. The second one is what's the impact of workforce size on processing time. So, for example, if one worker needs 5 minutes to do something, we need to see what would happen if 2 workers were allocated on this job, and how this processing time would be reduced. On the other hand, we may also have skill-based assignment when we have accomplished, of course, the first 2 points, which is that some workers may be more skilled in terms of doing some specific operations within the plant, but on the other hand, they may also be we may also have other workers which are more skillful in other tasks. And finally, this is a very, very important topic in terms of creating a rotation strategy. So we need to ensure somehow that workers do obtain skill development and expertise, but on the other hand, we have to prevent them from boredom and fatigue. So this is a list of my publications, and that's all from my side. Thank you.